Kenan, you're muted.
Everybody is. All right, forget it. All right, give yourself 5 points.
I'm so sorry you took
Man, I've been just talking to myself for 5 minutes. Damn you guys.
I thought you were just checking the slides. I didn't realize that you were going through them.
Yeah, me too.
Well, I'm glad somebody has awareness enough to know that something is way off. All right, that's fine. Things are so tough to tell because I have to get a clean recording, I have to turn off everything. All right, I have to hide everything in essence. All right. All right, so remember, within the context of time travel, let's get back to that thing. All right, so what is it? Wormholes are necessary, right? So what's a wormhole? 2 black holes connected. So which means that let's just talk about black holes briefly. All right, the question is how big are they? Now, if there's a black hole, say about 10 miles from the surface of the Earth, it would engulf us all. Within seconds, we would probably just vanish completely. So does this mean that they're really, really big, the black holes? Or are they really small? All right, so it makes sense that they have to be big enough for us to fit into them. But some will argue that they're actually fairly small. So how small is real small? Like the size of the United States, is it the size of Chicago, Elgin? The size of a building, size of a room. All right, we can make it even smaller. Size of a basketball, a soccer ball. I don't know. Or just make it the size of a ping pong ball. All right, could it be that it's going to be the size of a marble, smaller than a marble? How about the size of a molecule? How about the size of an atom, smaller than an atom? How small can we get? The next question is, what would happen to you if you were to fall into a black hole? Where would you go? It's the same as the mass falling into a black hole. Where would it go, in essence? There are 2 answers that you can come up with regarding that question. It's like a plumbing system. Either you'll go to the center, clog it up, or you'll go right through it, right? Now, if you go to the center and clog it up, fine. That's an easy one. But what if you go through the center? Where would you go? All right, so where is the other side of a black hole? Where does it open up to, if that's the case? We got a bunch of questions. Number one, if there's a mass nearby, it's going to get sucked into a black hole. All right, so here's a visual for you, not necessarily from the NASA website. I wonder if this guy's resume says a black hole expert. Now, the black hole theory, a lot of people think that's a new theory. It's not. You can trace the theory back to this guy. His name is John Mitchell. And in 1783, by looking at this formula, remember that the formula, we studied this formula extensively in Physics 1. It's the Newton's law of gravity. All right, so this formula explains why all objects follow at the same rate of acceleration. Everything's going to follow at the same rate of acceleration because that rate depends on the mass of the planet and inversely related to the square of the size of the planet or a star or whatever. All right, so multiplied by your mass is going to give you your weight. So in essence, this is going to give you the strength of gravity. Everything's going to follow at the same rate. All right, so John Mitchell was thinking, he thought to himself, what if there are stars out there which are just so incredibly massive? In fact, they're so massive that even light may not be able to escape from them. Now, if light is not escaping from a star, you're not seeing that star against the pitch darkness of the universe. So he came up with the concept of these dark stars, frozen dark stars, being invisible to us. All right, so that was the first attempt at something which is similar to black holes. And then we go a few years forward. So this is 1783 to 1795, more than a decade later. Another guy looking at the same theory comes up with a slightly different conclusion. This guy's name is Laplace. This guy is a French mathematician and a physicist. And this is a picture of him, kind of looks like Washington. All right, so this must have been the fashion of the day to look like that. He's writing a book on Newtonian physics. And he gets to the chapter regarding Newton's law of gravity. And he knows that the formula is correct. The reason why the reason why he knows the formula is correct, because formula makes the correct prediction for the acceleration due to gravity on Earth, which is 9.8. Everything is going to fall at a constant rate, roughly about 10 meters per second squared, precisely 9.8 meters per second squared. This question is, what if you shrink the size? All right, just shrink the radius. Keep the mass the same, shrink the radius. Now let's check to see what happens. So let's shrink the size, the radius of the Earth, make it about a mile. What happens to the gravitational pull? It jumped up. Now it's 155 million meters per second squared. So what does it mean? That means that you're feeling 15 million times heavier. Well, let's keep shrinking it. Okay, because we're doing a thought experiment. Just keep the Earth, the mass is the same. Let's shrink it. All right. Now make the radius about a meter long. That's about 3.28 feet. Again, the gravitational pull jumped up. Now you're looking at 400 trillion meters per second squared. You're feeling 40 trillion times heavier. All right, just keep shrinking it. Make it the size of an atom. Now the gravitational pull jumped up again. Now this is going to be 4 trillion times, trillion meters per second squared. Under these circumstances, the gravitational pull becomes so strong that the matter is going to start to collapse in on itself, which means that the radius is going to start to tend towards zero. And when the radius starts to go to zero, gravitational pull is going to become nearly infinitely large. Thus, you created yourself a black hole.
You can be forgiven for thinking a black hole is some sort of weird science trick. An infinitely small, invisible star defies common sense. It's what happens when you use mathematics as your lens on the universe.
At its center, black holes are infinitely small. They're not zero. They tend towards zero. All right. So they're going to be smaller than the smallest atom in your body. We don't know how small, let's say, but that's the reason why we say infinitely small, which means that the radius tends towards zero within a black hole. All right, so D is the best answer. All right, so okay, so the Laplace had this prediction in the first edition of his book. He said there must be stars out there who are so small that they must be generating tremendous amount of gravity. He didn't say black hole theory or whatever. He thought of some stars which are so infinitely small with large masses that they may be generating nearly infinite amount of gravitational pull nearby. His friends, needless to say, they were a little bit alarmed. He said, you're talking about things which are smaller than atoms, generating nearly infinitely large amount of gravitational pull? He said, that's nonsense. I mean, it's okay to think about these kind of things, they said, but don't talk about them, and certainly don't write them down, because this guy was supposed to be a genius. Because no one's going to take him seriously if he kept doing that. I mean, if you have these kind of thoughts today, obviously medication is available. Back then, it was suggested that you just keep those thoughts to yourself. Because as far as his friends were concerned, this was just mathematical nonsense. And that sort of mathematics did not have any correspondence to reality. Laplace's argument, hey, it's a valid mathematical prediction, and which needed to be included in the book. So the first edition had that prediction, so it's the second edition. And then something happened, which is known as life experience, so he came to his senses. Eventually, that argument was taken out of the book in the later editions completely. And then Einstein publishes his own theory of gravity in 1916. And this guy who looks like a comedian, he's not. This guy's a theoretical physicist, Karl Schwarzschild. In the middle of World War I, the Great War, he's in the German military. And because of the fact that he was considered to be a physicist, a bit of a genius, they decided to put him in charge of trajectory competitions for artillery. So the life is born. So Einstein publishes his own theory in 1916. He gets a hold of Einstein's paper, starts messing around with it, only to discover that Einstein's theory of gravity makes the same prediction of these infinitely small stars generating nearly infinitely large amounts of gravity. He gets all excited. He writes a letter to Einstein, including his mathematical proof.
World War I had just broken out when Albert Einstein publishes his general theory of relativity. Among those fighting on the Russian front is a German astronomer and physicist named Karl Schwarzschild. With a war raging around him, Schwarzschild discovers that Einstein's equations predict the existence of a star so unimaginably dense that even light cannot escape it. From the battlefield, he sends Einstein his calculations. Just weeks after receiving Einstein's reply, Schwarzschild dies on front lines. Einstein marvels at Schwarzschild's work, but he never accepts that such a star could really exist. As he puts it, it just doesn't smell right.
Einstein, unlike Laplace, was a genius. All right? He was a genius because he looks at it, he says, this is a mathematical prediction. It comes out of math. This sort of mathematics does not have any coincidence or correspondence to reality. Dismisses it immediately. He marvels at the solution that the Schwarzschild came up with. And he looks at it and says, yeah, it's just math. He ignores it. Einstein had a lot of common sense. He ignored it. He said, nope, that kind of mathematics does not correspond with reality. Now, lesser physicists, because they're no Einstein, obviously, took it seriously. And then they started developing this theory in 1916 on. Eventually, this guy came along. His name is Chandrasekhar. This guy is an Indian theoretical physicist. And then he kept working on the theory until the theory made observable predictions. And finally, in 1978, the first black hole was discovered, for which he won the Nobel Prize in 1983. All right, so you will keep hearing the term Nobel Prize, Nobel Prize, Nobel Prize. Guys, it's not a Nobel Prize, it's a Nobel Prize. This has nothing to do with being noble. It's a Nobel Prize, it's somebody's name. It's just about the biggest accolade that you can earn for yourself, and provided that you're not from the United States, for your country as well. All right, this sort of stuff is taken very seriously. So this guy is an Indian theoretical physicist, took it seriously enough to work on the theory until the theory he developed made observable predictions, for which he won the Nobel Prize in 1983. So this was a great learning experience for Einstein and the rest of the physics community in general, which is the stuff that I've been telling you forever. Common sense is no substitute for education. And it's no substitute for what nature usually comes up with. It's weird. If there's a mathematical prediction today, we take it seriously because nature appears to be very mathematical. Deep down, it's kind of weird. And because we put common sense aside, all of a sudden we will get into modern physics, which is going to be so bizarre that your common sense is not going to have any place in it. It's so weird.
60-second adventures in astronomy, number 12, black holes. DIY tip 34, how do you make yourself a black hole? A black hole occurs when something has so much mass in such a small space that nothing can escape its gravitational pull, not even light. In 1931, Subramanian Chandrasekhar calculated that if a star is big enough, when its fuel runs out, there is nothing to stop gravity from making its core collapse to create a black hole. Unfortunately for Chandrasekhar, his contemporaries, like Sir Arthur Eddington, just didn't believe him, but it turns out he was right, and in 1983 he eventually won a Nobel Prize for it. So if a star is big enough to begin with, when it collapses it becomes so dense that its gravitational pull won't let objects or light escape. In fact, you'd make a black hole if you crushed any object until it was small and dense enough. But you don't always have to crush something to make a black hole. The bigger one is, the less dense it needs to be. So you could make one out of tap water, though the required amount will fill the space between the Sun and Jupiter, and sadly there's not enough water in the galaxy for that. So for you DIY enthusiasts, you'll probably have to order it in specially.
We had this meeting at the Institute of Space Physics in New York. I said before we reach a final conclusion, we ought to throw into the pot still another object, a gravitationally completely collapsed object. Well, after you've used the phrase, a gravitationally completely collapsed object, 10 times, you conclude you've got to get a better name. So that's when I switched to the word black hole.
The word black hole, which John Wheeler coined, suddenly caught on. Everybody adopted it, and from then on, people around the world, in Moscow, in America, in England, and elsewhere, could know they were speaking about the same thing. And not only that, but it suddenly the whole range of concepts got through to the general public, and even science fiction writers all of a sudden could talk about it.
We had this meeting.
All right, the only thing new about the black hole theory is its name. The theory has been around almost 300 years, obviously. All right, the name. Prior to this guy, his name is John Wheeler. This is a name that you will get to know quite well at some point. Just about one of the biggest physicists who ever lived, did not have the honor of winning the Nobel Prize. One of the biggest and the most influential physicists, John Wheeler. This guy is John Wheeler. This is the guy who coined the term black hole. All right, instead of using the term black hole,
at the Institute of Space Physics in New York, I said before we reach a final conclusion, we ought to throw into the pot.
Instead of using the term black hole, they used to use a description instead of a name,
still
which happens to be
object, a gravitationally completely collapsed object.
All right, so gravitationally completely collapsed objects, and he's thinking, all right, let's call it a black hole. It caught on. All right. He's done a lot more than that, obviously, that you will get to discover. And then something else happened in the 1960s, which was instrumental, which will be instrumental to our discussion. Number one, this guy Hawking, obviously, was working on his PhD dissertation, which was related to the black hole theory. And a second guy, Penrose, started publishing his theories regarding the black hole theory. Okay, so these two, Hawking and Penrose, constructed our modern understanding of the black hole theory together. All right, so Hawking, obviously everybody knows who Hawking is. He passed away about 2 years ago, and he started publishing books in the 1980s, and then became really, really famous. And part of the reason why he became so famous, because obviously the way he looked, and he was wheelchaired, and he couldn't use his hands or his body, and this guy's a genius, obviously. It's because his publisher would not allow him to use any mathematics. So he was kind of forced to explain stuff, and his original books were not very understandable, and eventually he ended up getting pretty good editors, and his books all got better. Penrose, on the other hand, is just as famous, and he publishes just as many books. The only difference between Hawking and Penrose is, I don't know what kind of a publisher he has, his books are very mathematical. I don't even know why people bother to buy his books. I wonder if people just want to look smart or something, because his books are really tough to read. Even if you're a physicist, unless you're a theoretical physicist, his books are extremely difficult to read. And Penrose actually won the Nobel Prize last year in physics for the black hole theory. All right, so our modern understanding of the modern understanding of the black hole theory is going to be traced back to these two guys. So Hawking, that was his PhD, and Penrose. All right, and they kind of came up with the same theory that we've been using. It's very visual.
As the massive star contracts, its gravity becomes so strong that light can no longer escape. The region from which nothing can escape is called a black hole, and its boundary is called the event horizon. One might say of the event horizon what Dante said of the entrance to hell. Abandon all hope, ye who enter here.
All right, so the black hole theory kind of looks like that. So this thing that looks like an ass, I'm going to say, is a hole in the middle of it, opening in the middle of this called the singularity. And two-dimensional, what looks like butt cheeks, three-dimensional is going to look like a cone. All right. So this would be the opening, the boundary of a black hole. This is known as the event horizon. All right, so singularity is going to be the center. Singularity is going to be smaller than the smallest atom in your body. And the opening is known as the event horizon. And it is so named because once you get past the event horizon, no coming back out. Gravitational pull within it is just simply so strong, even light cannot escape from it. So if you're looking at it, if you're hovering just above it and you're looking inside, it will look pitch dark in essence. This whole contraption that you're looking at is known as the black hole. All right, so next question is, what is this the shape of? Well, that's the space-time continuum. This comes out of Einstein's theory of gravity. All right, so if you can just warp the space-time continuum into the shape, it's known as a black hole. All right, so that's the modern theory of a black hole. So the question is, how do we even know that they exist? And that's a valid question, because black holes are not green, they're not white, they're not yellow. They're black against the pitch darkness of the universe. How do you find something which happens to be black against the pitch darkness of the universe? How does that work?
But out here on the high desert of New Mexico, they found that black holes do exist outside of equations. 27 giant radio dish antennas, each 80 feet wide, are positioned over 13 miles to form a single huge radio telescope. They call this very large array of antennas the VLA, which stands for the Very Large Array of Antennas. James Moran is one of the world's foremost radio astronomers.
The VLA has had a tremendous impact over the last 15 years. It's very important because it has tremendous versatility. This technique of radio interferometers was developed after World War II, but this is the first really big array. Dust obscures light rays, but this instrument can penetrate that dust because radio waves go right through the dust, and we can see down to the core of things that can't be seen in optical astronomy, for example.
It turns out that a black hole can create radio signals as it sucks in matter. The signals can show up as a beam of microwaves, a microwave laser, or
maser. All right, how does that work? Okay, so there are a couple of ways we can detect black holes if we cannot see them directly. Number one is the most common way of looking at it. Guys, look, the moon orbits the Earth, right? Instead of going in a straight line, the moon actually makes a circle. The reason why it makes a circle is because it gets pulled towards the Earth by gravity. That's it. And the Earth orbits the sun, if you're looking at it, once again, for the same reason, because of gravity. Instead of going in a straight line, it's just going to keep orbiting. So imagine that you're looking at a two-star system, except you only see one of the stars. And when one star is doing this, it's going in a circle, meaning that it's orbiting something else. If you don't see the second star, all of a sudden you go, oh, it's orbiting a black hole. That's one way of doing it. The second way of doing this stuff is the masses will get sucked into a black hole. All right. And one thing that we know about these masses is they are moving towards the black hole, they will accelerate, which is fine. Masses are composed of molecules, molecules are composed of atoms, the atoms are composed of charges, and the accelerating charges will radiate electromagnetic waves, right? So they will radiate electromagnetic waves, they will radiate energy in the form of electromagnetic waves. So from these objects moving towards the black hole, we're going to get tremendous amount of radiation in all parts of the electromagnetic wave spectrum. All right, so these guys are using radio wave and microwave telescopes. Microwaves and radio waves, extremely large wavelengths, which means that they will see right through the materials, right through the clouds. All right, the radio waves go around buildings and all that stuff. Obviously, you're able to hear, you're able to listen to your radio as a result. Microwaves do the same. That's the reason why you're able to communicate with other people using your cell phones. All right, and the space-based telescopes tend to be ultraviolet, X-rays, gamma rays, or whatever. They include everything, but the Earth-mount telescopes usually go up to visible light, and that's the extent of it. All right, so objects, as they're being dragged towards a black hole, they will radiate energy in the form of electromagnetic waves. So we're going to end up getting a tremendous amount of radiation near a black hole, and so that's how we know, and that's what they were talking about. All right, so but there's more to the story.
Hubble has put some of astronomy's most treasured imaginings to the test. What Hubble did was look at the center of a galaxy where we suspected there might be a black hole. A black hole is an object that is very, very dense and very, very small. So dense and so tiny that the speed of escape from that object exceeds the speed of light. So nothing can get out of it. Everything just gets sucked into it and disappears from the universe. Black holes have been fantasy and science fiction for decades. And what Hubble has done now is it's shown us that black holes are scientific fact.
The audio is recorded. It just
That's fine. Let's fix that. Is it better?
Yes.
Okay, awesome. Thank you. Give yourself 5 points. All right, so one of the things that I want you to notice is, guys, this is what a black hole looks like. You go, no. Black hole is supposed to be black. And this thing is not black. This thing is white. Not only is it white, it's actually fairly bright. How's that possible? And all of a sudden you go, somebody messed something up. It's supposed to be black. It doesn't look black. It's not black. It cannot be black. Did we get the colors wrong somehow? What's going on?
In the long history of the universe.
What are you guys looking at? You're thinking, I'm looking at a black hole. I'm thinking, no, you're looking at a spiral galaxy. And you're looking at a negative image of a spiral galaxy. What do you have at the center? And you're thinking, we have a black hole. Well, you can't, that's not how you do physics. So let me explain what you guys are looking at and the reason why we're looking at a negative image. All right, these dots that you're looking at are star clusters. Every single cluster that you're looking at is probably going to have billions upon stars in it. And then the entire galaxy is moving about a common origin, meaning that whatever's at the center is generating a tremendous amount of gravity. As a result, you end up getting this circular motion, right? In the absence of that gravity provided by whatever's at the center, these clusters would have been moving in a straight line at a constant speed. So these clusters are experiencing a force directed towards the center, which means that the center is generating tremendous amount of gravity. And if you look at the colors, in this case, because you're looking at the negative, notice that the center is actually fairly dark, which means that it's actually fairly bright. All right, so at the center of each and every single spiral galaxy, you're going to have a giant black hole keeping the galaxy together. So the question becomes, how come it's bright? What's going on? I mean, it's because we thought that the black holes were supposed to be black. Well, I got news for you. They're black. There's no question about it. If you're right above the event horizon, if you're just doing a flyby, and if there's nothing nearby falling in, it's your lucky day and nothing is falling in. It's completely empty space. So you go, okay, it's my time. I'm going to take my fourth tempo and I'm just going to do a flyby without getting sucked into it. All right, at the right escape velocity. And at that point, if you're looking in, you're not going to see anything because nothing's going to be coming out of a black hole. It's going to be pitch dark. That's what it means. So why then it looks bright? Why then it looks really, really, really white? It's not the black hole that looks white. It's the stuff which is falling into it, guys. So what happens? It's accelerated charges will radiate energy in all parts of the electromagnetic wave spectrum. And then you will see the visible portion of that spectrum. So the falling objects will simply glow. And then you got stuff keep falling into it continuously. As a result, everything is going to light up just above the event horizon. So that's what you're looking at in essence. All right, so near a black hole, anything near a black hole is going to be getting sucked into it. As they're accelerating towards the black hole, this entire space is simply going to light up. All right, so that's the other way to know that there's a black hole there. All right, look at this. I mean, the center of the galaxy is going to be the brightest portion of the galaxy. All right, so the next question is, how did they form? What do we get these black holes?
When enough matter collects, gravity is strong enough to squish hydrogen atoms into helium atoms. This fusion releases enough energy to turn on a star. But gravity is also a star killer.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart. And for about 90% of the life of the star is in nearly perfect equilibrium. And it just sits there, burning away and producing radiation.
But when the fuel is gone and fires go out, gravity is free to collapse the star. A medium-sized star like our sun will burn steadily for 10 billion years. Then, in a kind of cosmic spasm, it will puff up to engulf the inner planets before collapsing into one of those white dwarf stars. A star twice the mass of our sun would collapse even farther, ending up as a super-dense star the size of New York City, a neutron star. A teaspoonful of stuff from a neutron star would weigh 100 million tons. But what happens to a bigger star when its fires die down? Say a star 50 times the size of the sun. It may blow up as a supernova, leaving a neutron star, but then it keeps on shrinking to infinity, an infinitely small point with a gravity so powerful that not even light can escape.
All right, so stars, depending upon their sizes, if they have the proper initial sizes, may collapse into a black hole when they run out of their nuclear fuel. What fuels a star is fusion. It's hydrogen fusing into helium. Once you run out of hydrogen, that's it. At that point, gravity becomes the dominant force. The stars may collapse into black holes, and so that's how they form. So the next question is, what happens to the mass falling into a black hole? Where does it go?
A black hole can attract dust and gas in its neighborhood into a whirling disk of molecules. Those molecules release great bursts of radio energy as they are drawn in. There seem to be black holes made not from single stars, but from whole clusters of stars. They have a mass 100 million times that of our sun. But these monsters are still infinitely small points, capable of gobbling up other stars. But where does the stuff that falls into a black hole go? Does it just fall out of the universe? Possibly. Or it may pop up somewhere else in space. If you'll excuse an indelicate metaphor, there may be white holes regurgitating matter eaten by black holes in another part of the universe, a wormhole in the fabric of space and time, allowing you to go from one location to another without crossing the space in between. Or it might go to another universe entirely. Astronomy's reigning theoretical genius, Stephen Hawking, proposed that the black holes in our universe might well give birth to other universes. In fact, there might be any number of universes, like bubbles in the bath.
All right, so according to the original theory that Stephen Hawking came up with, or original theory that they constructed more like in the 1960s, we would have static black holes, meaning that you fall into it, you would go to the center, clog it up, it would get more massive. So the mass would become crunched. The more mass you squeeze at the center, the bigger the event horizon would become. That's it. That was the way they were looking at it. Eventually, we started discovering these black holes, and every single black hole discovered appears to be a spinning black holes because they're spinning and rotating. It's the center, as small as the center may be, it's still going to be large enough for something to go through. No mass is going to go through. The mass is going to get crunched up. And when it gets crunched up, of course, it turns into energy. So what goes in from this end must be coming out from the other side of a black hole. And when it comes out, it's going to come out in the form of energy. So once again, we're going to end up getting all parts of the electromagnetic wave spectrum. So the portion of the spectrum that you can see is the light spectrum, in essence. And so you're going to see all the colors at the same time. So it's going to look white to us. Okay, so that's one theory. So if the mass goes in and gets converted into energy and leaks out from the other side of the black hole, and they refer to that as the white hole, okay, the question becomes, where does it open up to? At that point, obviously, you have speculation after speculation, and each speculation becomes a book. In the case of Stephen Hawking, all right. So, what's a black hole from this end can become a Big Bang in a different universe, starting a new baby universe, or it could be a shortcut within the space-time continuum, by taking the mass and turning it into energy and leaking it to somewhere else in the universe and creating all these quasars. That's another way of looking at it. The third way of looking at it, it becomes a shortcut, theoretical shortcut, it turns into a wormhole, in essence, allowing time travel. Okay, so regardless of whichever interpretation that you're looking at, one fact remains, guys. What happens beyond the event horizon is unknowable and remains unknowable. Because no information, nothing comes out of a black hole. Nothing can escape from a black hole. All right? And that's the reason why I decided to name my course Beyond the Event Horizon. That became an investigation about time travel and the possibility of the parallel universes. All right, so we got speculation after speculation. The only way you can probe into a black hole is through mathematics. And that's the game that we've been playing for the past, 40, 50 years. And the final theory that we came up with is known as the string theory. Okay, so it's a combination of Einstein's theory of gravity and the quantum theory. And then we will cover those things. The other thing that I'm going to mention is this guy, John Wheeler.
We had this meeting at the
I said this guy is
Institute
important
of Space Physics in New York.
for many reasons. Because just about everything that we will discuss is going to go back to this guy. Case in point, Kip Thorne, for example. What's his relationship to John Wheeler? Well, he ended up getting his PhD under John Wheeler. All right, and Kip Thorne didn't come up with the theory of wormholes. John Wheeler did. Okay, that was his theory. In fact, John Wheeler wasn't even thinking about it. He just, when these guys were developing the theory of gravity, and Kip Thorne was working under John Wheeler at the time, and all of a sudden, John Wheeler looks at it. He says, you know, what if you have a black hole today, and then it becomes connected to a black hole from the future or the past? And immediately they knew that that would be a shortcut to the space-time continuum, right? So they contemplated it. They looked at the derivations, and they didn't put too much thought in it, in essence, because if there's connection, if you got two black holes connected somehow, in theory, it would be a chance connection. Number one, that connection wouldn't even last that long. It would just, it would become disconnected. So that didn't mean anything. And it was just one of the mathematical conclusions that they came up with. Neither one of them took it seriously. And then, I don't know, John Wheeler decided to shelve it. It wasn't a big deal. So one of the solutions, and then they had this paper pile, and then just put it on top of a shelf, and that's the extent of it. And then years later, in 1985, Kip Thorne is obviously listening to Carl Sagan, and then Carl Sagan has all these questions. He wants to know whether or not it's possible to travel a distance of a place which is 26 light years away within a fraction of a second. And then eventually Kip Thorne goes, wait a minute, he kind of vaguely remembers that they came up with that bizarre solution at some point. And then he kind of remembers that John Wheeler called it the wormhole, in essence. The guy who coined the term black hole also is the same guy who coined the term wormhole. Another guy who got his PhD under John Wheeler is this guy, Hubbard III. And this is the guy who gives us the main world's interpretation of quantum theory. So this is the guy who introduced the time travel into physics. Somehow, this guy's theory is going to be required for time travel to be possible. And these two guys got their PhDs under John Wheeler. All right, so this guy won the Nobel Prize 3 years ago or 4 years ago, I forget, for the LIGO project. So what LIGO is something that we will discuss later. And there was another guy who got his PhD under John Wheeler, and that guy is Richard Feynman. Just about the best physicist who ever lived, next to Einstein. Remember the movie, The Infinity? It was about that guy. And that guy also had Nobel Prize in physics. Right, so